feature engineering. Okay, now this feature engineering is related to the features. Okay, what is feature means? Feature here refers to the independent variables. Independent variables. Independent variables. What is independent variables? In a data set, any data set, we have one output column or a target column, and rest each and every column which every column, okay, values which are responsible for creating an output, is terms to be features. Okay, is terms to be feature. For example, this x1 column, this record x2, x3, x4, x5, x6, this record is responsible for creating this y output. Okay, then we say these are features. And this features, so if this feature is so important because it is playing a role, okay, in giving us an output, or it is in relationship with the output, so we should give some importance to these features, right? We should give some importance because our output is dependent on these features. Our output is dependent on this features, right? That's why output is also known as dependent variable. Output is also known as dependent variables. It means features are very important. So one thing to note, then we should take care of features, like only significant features should be provided. Only significant features should be provided to the model, right? And if you have provided the significant features, then is there any multicollinearity or not? We should check multicollinearity. You can check with the correlation or with the inflation variance factor. Inflation variance factor, right? You should also see, okay, about the scaling of it. Scaling, what is scaling? We'll see into that one. After that scaling, if everything scaling is done, then we should see whether any categorical variable is there or not. If it is, that proper encoding should be done. Okay, so what is encoding here? We'll see. Today we will learn about the scaling factors and the categorical factor if possible. Okay, so why even scaling is required? This is the part of feature scaling. There are some others are also part of feature scaling. Okay, but on a broader umbrella, yeah, these are some of the steps that we look into the feature engineering, because features are very important for our output, because our output is totally dependent on the features. Okay, they play a vital role in creating the output. So if we want an accurate output, if we want a very high accuracy, then you should provide a right accurate variable in a proper format, right? Because let's take an analogy, like if we want to be very healthy, right? Healthy means we should give more output. If we will give more output, then people see like we are very healthy. Like if we are running in a running a lot, we are studying, we are doing our daily exercise, we are doing our daily activity in a proper way, okay, then people see and say that yeah, you are a healthy person, right? To be unhealthy, we require an inlet of right proportion of nutrients, foods, okay. So then if input is right, then output will be right, right? The same way it is. So if you in a data set, if you require a proper output, you should give a proper input, and that type of process and that type of engineering in this one is termed to be known as feature engineering, where we work on the features only. We try to provide the best and best features, okay, so that we can have the proper output, okay. Now, so we'll go and learn about the scaling part first, okay. Why even scaling is required, and if scaling is required, then what are the methods by which we can do the scaling part, okay. And after doing scaling, are we getting a better results or not, and what happens when we do a scaling? This should be the some question that you should have in your mind, okay. So before starting a scaling, let's dive into a original data without having a scaling part, okay. And then we will see the pros and cons, and then we will move into the scaling part, okay. Why, then you will understand why scaling is required first. Second will be, if scaling is required, then what are the different methods that by which we can do the scaling part, okay. Okay, fine. So first we will move into second will be, if scaling is required, then what are the different methods that by which we can do the scaling part, okay. Okay, fine. So first we will move into a normal data set. Okay. For example, let's see, we have this data set, okay. This is university data set, okay. So this university data set tells us about, first column is university, state, SAT, top 10, accept, SF ratio, expense and grade, okay. This is basically university name, this is the state, this is the SAT score, this is the acceptance acceptance ratio, this is the student faculty ratio, the expense into that particular university, and the grade rate of that basically university. And you can see different universities has different values, right? Am I clear to you all, right? Now, so there are certain algorithms, okay, there are certain algorithms in machine learning, okay, which depends on distance, for example, okay. Or let's you know a distance formula, you know a distance formula, right? What is distance formula? Can anyone tell me? Let's do one first. Distance formula. So you know the distance formula, right? If you have an axis, okay, this is y and this is x, and you have a point over here, the coordinate will be x1 and y1, and this is another one, you have a x2 and y2. If I tell you to find a distance between this point, let's say example A and B, okay, how will you find? You will do it, just you will Yeah, you will use the distance formula x2 minus x1 का whole square plus y2 minus y1 का whole square. This is the same thing that you will do, and you will come up with an answer, right? That this is our distance between these two points A and B, right? Now just try to understand here. In machine learning, there we had only two axes, one y and second one was x. But in machine learning, every, let's not see this two, for example, for now. Okay, let's hide it. We'll see the number parts only. Every column plays a role of an axis. Every column plays a role of axis. Getting my point? If let me tell you, if we have a data, okay, like data, right? How we see a data in mathematics. This is x1, this is x2, this is x3, this is x4, this is x5, this is x6, and for example this is x7, right? In maths, each and every column is an axis. For example, here we had x1, x2, x3, x4, x5, right? Then we had y1, y2, y3, y4 and y5, right? So we plotted this two, right, with two-dimensional data, right? If we had three-dimensional, z1, z2, z3, z4, z5, so we could have given like this one. This is z, okay, and you could have used, but this is we till now we were limited to the three-dimensional, but we can have one more axis, x, y, z, then let's say a, and then again after that b, but we can't see those things into two-dimensional figure, right? This is our two-dimensional sheet, right? But we are able to create a three-dimensional by saying that it is a z-axis that is coming out from the xy plane, right? And we are basically assuming that z is outside the xy plane and it is denoting a z-axis, okay, right? Similarly, in a mathematics, the data set is taken as a, each and every column is taken as a axis. Each and every column is taken as an axis, okay, and their points reflects their data points. For example, this is a, so if we are talking about a two-dimensional data, then this is a, and this is a, right, and this is b, right? Then this might be another one, right? If you are talking about three-dimensional, then we require three coordinates, right? Then it will be x1, y1 and z1 to say something in one record, okay, x2, y2 and z2. If we have 4, then this entire will be termed as one set of data or one point. Am I clear to you all? Right? So that's how a data set in a machine learning algorithm is taken care, and this is known as the vectors. These are known as vectors, okay, vectors. Now try to understand, okay, Now if I say to you, right, this is, I am having this much column, so this entire record will, let's assume, representing a point a, this entire point data points of x1 x2 x3 x4 x5 x6 x7 represents a, and here entire data point, this entire data points refers b, right, refers b, right. Then if I tell me the distance between a and b, tell me distance between a and b, the same way, like this way, then you will again use the same formula, right. Only x1 minus x2 का whole x1, this is not x1, that's take it like not x1 x2, you will get confused, okay. Instead of that, just let's take it like okay, let's take it this is a column, b column, c column, d column, e column, f column and g column, and this is having x1 का value, x2 का value, okay, and this is having y1 का value, and this is having y2 का value, z, and similarly, right. So what you will do, you will subtract x1 x2 का whole square plus then this with this one, then y1 minus y2 का whole square, then this or this, or instead of that let's take it like that one, no? It is very easy, that very very easy. Yep. Instead of that, like this one, let's take the column name itself. Let's take column name like a1 minus a2. Let's take this is first record and this is second record, right. a1 minus a2 का whole square plus b1 minus b2 का whole square plus c1 minus c2 का whole square plus d1 minus d2 का whole square and so on till g1 minus g2 का whole square. Am I clear to you all? Right, then whatever the answer will you have, right, that is the distance between these 2 points, because each and every column is playing a role of dimension or a axis. That's why it is known as features, also known as dimensions. Features are also known as dimensions. Okay, very good. This is one way, okay, of writing and telling the distance between two particular records. Okay, for example, now let's assume you have different values into the a b c d e f g h column, okay, h is not there, till g, different values, okay. Now don't you think like each value will have its contribution in finding the distance, right? Okay, now try to understand, if for example a is a column that is starting from thousands, for example, that is starting from thousands, okay, and b c d e f and g are columns that are basically having a values in units, okay, 1 unit or 2 digit maximum. Alone a is having value in thousands. So don't you think, or not even in thousand, let's take a has a value which is either having 1000, either having 2 digit, either having 1 digit, and so on. There's lots of variance into the A. So don't you think the value of A is going to affect the distance for each and every record? Because each and every column value is responsible in creating a distance. First thing. Second thing, now if A is having value starts from 1000 itself and others are in 2 digit or 1 digit, so don't you think they are not on the same scale? Right? First thing, they are not on the same scale. Okay. Second thing to be noted, then machine learning algorithm will give more preference to this A column. Don't you think so? Because they will understand the numbers itself only. They will understand the numbers. Okay. So if these are in different scale and this is in different scale, right? And this is on a higher number side, then machine learning algorithm might understand this is more weightage column. This is more weightage column. Although it is there or not, that is a thing that we need to find, but machine learning algorithm understand na, it is a more weightage column and it will give more importance to this column. For example, right? So there is a column A, B, C, D. Okay. This is starting from 1000, 2000 and so on, and this is something else. Okay. Now try to understand. This is a person 1000 is earning at a salary at an age of 35, but a person which is earning 2000, okay, at an age of, let's take example, it is 35, then let's take it as 30 for example. So don't you think this person and this person is having a different salaries, okay, at different age, right? And we should consider this one also, who is better one, who is getting higher salary at what experience and other things. But if you'll place this entire data into machine learning algorithm will provide less weightage to this column than this column. Why? Because this column is having high values, right? More high values, so more weightage will be given. They will understand that is a having high value, then it is a more weightage column. But it is not, because everything 1000, 2000 something, this is supposed to be like that, because salaries always remains like this one, this thing only. There is nothing like high weightage of this one, right? Salaries are like this and age is like this only. There is nothing like it is high weightage or low weightage. Getting my point, everyone? Right? So we should understand that we shouldn't give priority before ingesting data into machine learning. Okay, so that to remove this type of thing, we use scaling. What scaling do? Scaling basically standardize the data. And there are various method. Okay, it standardize the data. Okay, it provides the data into one scale. Once you are on one scale, okay, and if you are having a value greater than me, Good. There is no doubt that you are better. But try to understand. If you are on a different scale, I can't compare to you with me. Are you getting my point? Whether you are better or I am better. First, we need to come on a common scale, each and everyone, right? Then we can go for the modeling part, right? So we need to find, we need to see into a data. Once we have a data, so always we need to find and we need to see that if this is a column A, B, C, D and E, how many, what are the values are A into B, C or D or E? If they are different values on a different scales, right? Like for example salary and age. Salary will be always into thousands, right? And even lakhs, okay? And the age will always under the 100 or even 60, because the retirement is 60, right? It is always below 60. So both are not on the same scale. For an algorithm, machine learning algorithm, data is a number. Data is not, he doesn't know how to compare both the data. He understands the number itself. That's all. It's a number, it's a high value number, it's more weightage. It's a low value number, it's a less weightage. For example, you got 100 number, I got 5 number. Okay. So it means I'm bad, you are good. That's how a machine learning algorithm compares. That's all. Logically it will test. But it may be I got 5 out of 6 and you got 100 out of 200. Now who's better? Tell me. Of course me, na. I got 5 out of 6, right? And you got 100 out of 200, right? This is B, a person who got 5 out of 6, and a person A who got 100 out of 200. But since you have 100 over here, the machine learning algorithm will give more weightage in calculation of distance. Getting my point? It will play a vital role in this calculation, distance calculation. Are you getting my point? Right? So that's the reason we should be on a same scale. We should bring a person into a data set on a same scale. Then only we can compare who is better and who is not. Right now we of course we can say 100 is better than 5 number wise, but out of what? We are not on the same scale. Yeah, we are not on the same scale. Getting my point? So we should bring every data set points onto a same scale. For that we do the scaling, so that, why? Because so every independent variable, because every independent variable plays a vital role in creating the output, right? In creating the output. So we should provide input in a very proper format, right? That's why we also provide the features into a proper scale, so that now algorithm can understand which is better, which is not better, which feature has higher weightage and which feature has lower weightage. Okay, that's why we do the feature scaling, so that algorithm can understand the data in a better way, right? Now scaling, standardize, so that we can bring on a one scale. Now we understood the use of scaling, why even we require scaling, why even we want to particularly standardize a data, right? Then why to bring into one scale, we understood that part. Now we'll understand how to do that, how to do that, right? how to perform scaling, right? So there are various methods. Okay, one of the method is same method that we have learned in the statistic also, and we will also see here also, and that is known as, first method is Z transformation, that is also known as standardization. Standardization. The formula for this one will be xi equals to, tell me, x instead of, let's, for the zi, let's take it as z1 is equals to xi minus x minus mu upon sigma, right? Where xi is the feature, mu is our mean, and sigma is our standard deviation, right? So let's, for example, if we have a data set, right, like 100, 200, 150, 90, 60, 75, 185, and so on, right? It's a data set. So what we will do, first we will find the mean of this data first, then we will find the standard deviation of this data. Okay, once done, then we will find 100 minus mean upon sigma, and we will find the z1. Then for the 200 we'll do 200 minus mu upon sigma, we'll get the z2, and so on. And we know that what we know, that this z1, okay, this z1, z2, z3, and so on till zn has a standard deviation of 1 only, and the mean will be 0. Yes or no? Right? Right. So what we are doing by this thing, so let's for example, I have a data which is having such type of distribution. Okay, such type of distribution. Okay, now what I am doing, okay, I'm pushing this data, for this is the data, so this is the total area of the data, or expansion of our data, right? So try to understand, this might be the mean, this might be the mean of the data. I'm not sure, this can be, but this can be the mean, yes or no, right? This can be a mean of the data along x1 and along y1 coordinate, right? So now if I transformed into Z transformation, so we know that in the Z transformation the mean is 0. So we have pushed this data here, and this is our basically our x may variance or standard deviation, and this is our y ka variance, yes or no, the spread of the data, yes, right? Now since we know that the standard deviation of this Z transformation is how much? 1 only. Then we are basically limiting our data. The data distribution will be same. The data distribution will be same. Just we have what we have done. We have basically limited our data. We have just limited our data or confined our data in a standard deviation of 1 only. Are you getting my point? It's 1 itself, only 1, whether in the x side or into the y side. Are you getting my point? Are you getting my point, everyone? Right? Very good. So let's use it now. Let's see. Okay, so now if we'll do this the same thing with all columns, if you do the same thing with all the columns, for example, you have a column, B column, C column, D column and E column, right? Every column. Now if we'll transform this all columns into, let's take an example, this is a dash column, this is B dash, this is C dash, this is D dash, this is E dash. Now don't you think after transformation, now each and every value into this columns are having mean is equals to 0 and standard deviation is equal to 1 only? Yes or no? Each and every column. Now they are on a 1 scale. Now if any value is greater, right, then we can say, yeah, it is greater. It is greater. It is something more. For example, 100, and we tried to compare 105 before. Now if we find 100, okay, का z1 and 5 का z2, now obviously z2 will be greater than z1, because we are finding out of 6 and out of 200. Now this z1 and z2, if we compare, z2 will be higher, right? So that's why we do scaling. That's why we do a scaling, and it is required. It is always required, and we'll see what are the different method into the Python by which we can do this scaling also. So first we will try to visualize it, okay, with this normal method, okay, and then we will use the sklearn for this one. Okay, we'll use sklearn for, okay. Now compare this data. Now are you able to see this? These columns were having a different 2-digit value. This for column also has a 2-digit value, but this column and this column was having a higher values, right? So don't you think this column and this column is not having a same scale, right? This column, this column, this column are on different scales, right? This column is highest value is how much? You can find it also, right? The highest value is around 69, I think so. Okay, the highest value is 69. Here it is 100. These are in the thousands. Okay, this is again into the 2-digit. This is again into the thousands itself, right? So each and every data set into a, what I can say, different scales, right? And it shouldn't be there, because if we will provide the data into different scale, right, in machine learning it will create a problem, because data points are not on the same scale, right? Now let's see. Okay, let's see. For example, let's calculate distance. Let's calculate the distance formula. For example, distance between this and this. Okay, so what I will do, first I need to import numpy as np. Okay, now np dot square root. Okay, then we need to provide the values. For example, this one. Okay, square root, done. Then let's use it like 1310 minus 1415, right? Ka square, right? Then plus this one 89 minus 100 chi-square plus, okay, plus 22 or 25, right? 22 minus 25 square plus 13 minus 6 chi-square plus 22704 minus 63575, right? Chi-square, right? And then we'll find 94 minus 81 chi-square, right? And whatever the value will come, and we have done the square root, right? So we'll have a value at like 202, right? And let's put it here like a is equals to this one, then a. So this is the distance, right? 2022. Let's use it into a by doing the standard scaling. Okay, so let's do it for this part only. Let's do it for this part, or you can use entire one itself. Okay, now we need to provide from sklearn dot pre-processing import standard scalar, right? Done. Now this standard scalar is the same for the Z transformation. Then once we are imported it, we need to instantiate it. Scalar equals to standard, or instead of that small की जगह पे standard scalar instantiated. Now we are having a object created for the standard scalar. Now we can use it. How to use it? We'll use scalar dot fit. Okay, x train, not x train. We'll use this df. Okay, we'll use this df. Okay, now it will calculate everything, all the values, mean, variance, everything. Okay, once we do fit, the fit calculates everything, whatever the data we have provided inside this one. Okay, after this we need to transform also. Fit never transform things. Fit only calculates and keep it with it. Okay, it never transforms. Now to transform it, let's take it like df underscore. Okay, now we have also provided, now just a second, df dot drop. Okay, in the drop let's provide this one univ, and because this is a categorical column, right, univ and state. Okay, state, right. Now this is x is equal to what, 1, right, and then transform form is equals to scalar dot transform. Now we are basically transforming our data. We are basically transforming. Instead of that, let's create the same thing like control. Let's do this one, control x, and let us put it here itself as control v, and let's put it as df underscore 1. Great. And then let's put it as here, right, and let's again put it here df underscore 1 for better visibility. Okay, now run it. We ran it. Now you can see df underscore transform. See the values. Are you able to see all those values? Now let's use it. How to do it? Like for example, df underscore transform. Okay, underscore 1. Let's use it at pd dot data frame. Let's use df underscore transform, right, and the column names equals to df underscore 1 dot columns. Okay, now let's compare. I will not compare over here, we'll just find it here, and let's compare by df underscore transform dot head. Now see, now are you able to see that all the values has come into a common scale? Now if you compare df dot head, now see, just ignore this too, right? Now just compare this and everything else. Getting my point, everyone? Now this is much more easier for our algorithm to digest which point is greater, which point is lesser, which to give higher weightage, which to give lower weightage. It will compare each and everything. Getting my point, everyone? Right? That's how it happens. That's how it happens, and the distribution always remains the same. Now this standard scalar, okay, this standard scalar always gives us the z transformation, and it never changes the distribution. It never changes a distribution. If you want to check whether it changes the distribution or not, let's see how to check. So let's create a data set, or if you don't want to create a data set itself, let's take one column of it. For example, for x, let's take a column df dot which one I should take? Let's take about expenses, right? right? We have taken expenses, x dot GAD head. Now you can see, okay, this is our data. Now if I do a scatter plot of it, if I do scatter plot, or the if you want to check the distribution of it, okay, how the numbers are basically what I can say, distributed, or how the numbers are basically everywhere, right? So how to see this? Tell me. You can only see that thing if you have a point, a coordinate. Coordinate means x and y, right? Then only you can have the, this is x, this is y, right? So each and every value is having a what value? Tell me. Each and every value is having a two coordinates, right? This is your x1 and this is your y1. Then only you can plot a scatter plot, right? Great, nice, okay, fine. So now let us find two things. Let's take x1. Let me just a second. Yeah, let us see. Let's take it like x1, right? Great. And let's take an SF ratio as x2. df dot SF ratio and x2 dot HEAD head, right? Now we have two variables, right? Both. Import matplotlib dot pyplot as plt. Yeah. Then plt dot scatter. Let's now you can see we can provide two values into this one, right? X and y, right? So let's see x1 and we provide x2, right? Now you can have a distribution, right? You have a distribution of this one. Now let's take the same thing but from the transformed part, okay? From the transformed part, let's use x11 equals to df transformed by, it was df transform underscore 1, right? Df transform underscore 1 dot SF ratio, right? And we will take x22 equals to df underscore transform dot expenses, right? Done. Then we will check the plt dot scatter and we'll provide x11 and x22. Try to understand. Are you, and let me put it here is like plt dot subplot. Let's put it like we want one row, two column, right? And let's put it first over here, okay? So let's use it, this one, control C, control V, and let's put plt dot subplot 1 comma 2 comma 2 by, let's use the same equation over here and let's put 1 and let's put 2, right? Done. Now just try to see. Just try to see. Do you think is there any change into the distribution? No, there's no change into the distribution, almost the same, right? Only it is compressed towards the center side. It is compressed toward the center side. Are you getting my point, everyone? We shifted this thing towards this thing, towards this point where it should have the mean as 0 and the variance as about 1. Getting my point? Now see this is the line. Are you getting my point? Are you getting my point, everyone? That's how it happens. Okay, that's how it happens. Okay, so this is known as standard scaling. Okay, you can also do this standard scaling by z equals to x minus mu upon sigma. That is what it do into this part. It is known as standard scaling. Okay, if you go inside the standard scaler to go into the doc string, you will find the same formula. Are you able to find this one? So you don't require to find the mu, the standard deviation. Okay, you just require to use this one and it will find each and everything, and we just provided all the column in one go. We'll provided all the column. Getting my point? See, df underscore 1 entire column, and it found the z1, z2, z3 for each and every column in just one go. So it is very easy enough for us, because if we need to do standard scaling for each and every column, first we need to find the sigma for this one, first we need to find the mu for this one, then we need to find z1, z2, z3 for this one, again for this one, then this one, then this one, this one, this one. Now we don't require to find, we just require to import standard scaler. Okay, we need to provide the data for which it should calculate all the value with the fit. Okay, it will calculate all the like sigma, or it will calculate all the value like mu. Okay, and then we provided the transform. Now a question comes up, like, can't we do fit and transform? Means we calculate and transform in one go. Yeah, we can do. We have a method known as fit underscore transform. For example, let's do scalar dot fit. Okay, now you have fit under transform. So in this case, what it will do, it will calculate and transform together. Means you don't require to write two different line of code. It will do, first it will calculate everything. Okay, then it will transform. It will create the z1, z2 and z3 ka value, and will put into the data, this data. Right now it just calculated, now it is transforming, because it's putting the z1, z2, z3 ka value here. Getting my point? Then again a question comes up, then why we have a separate thing, fit separate, transform they're separate, if we have fit underscore transform? Because in some time we require to calculate, but we don't require to transform. Okay, for that case we have fit and transform separately, right? But in some of the case we require, like here itself, if we want to fit and transform together in one go, we'll do that. Okay, any issue? Right? I hope I'm clear to you all, right? Okay, take care. So let's take one more example for, and we have other methods like normalizations also. Okay, so I'll not touch normalization right now. I'll not touch normalization right. Let's take one more example. Let's create a data for that one. For example, like let's create data is equals to np dot random, right? Dot random integer, and let's create a values like from 1 to 1000. Okay, and let's have 100 values. Okay, 100 values. So we have data, right? Let's, instead of creating manually, let's have this data. We have this data, right? 100 data points. Okay, now, so this is basically on a different scale. This is on the different scale. Are you getting my point, everyone? Right? They're totally on a different scale. Let's create one more data. Let's, for example, data 1. Again, take a value, control C, control V, and 100 value we require, but we require in out of 500, for example. Let's take it as like that. So we have data 1 also. Okay, again we have. Now let's plot it. plt dot scatter plot. Okay, and data comma data 1 plt dot show show. Now you have a very weird data set, right? Now let's use our standard scaling. Okay, now let's use it. Now we have instantiated standard scaler with the name of, I think, scalar, right? Okay, let's use it. Okay, scalar dot fit underscore transform. Let's put data, right? And let's put data transform underscore 1, and let's this one, and let's use second one, and let's put it as 2. Instead of this one, what was the data 1? Okay, let's put it as data 1. Okay, now let's use plt dot subplot 1 comma 2 comma 1. Okay, and let's plot this figure first of all. Control C, control V, and then plot control V, this control C, control V, control C, and control V. And before that, let's put plt dot subplot 1 comma 2 comma 2, and then use plt dot show something. Then we need to put it into the data set. It's df1 is equals to pd dot data frame. Then we'll put data underscore transform 1 slash columns equals to df columns. Okay, done. Yep, done. And now we will use this one, instead of not this one, control C, control V dot, first is data 1 and second will be df dot data 2. Yep, see, are you able to see the distribution is same? The distribution is same, only the scaling has been changed. Only the scaling has been changed. Are you able to see that? Right? That is the use. Means this Z transforms, a standard scalar or normalization that we will study, only changes the what standard deviation and put into the mean across 0. Now you can see 0 is here, right? So it is compressed towards the mean 0. Now are you able to visualize this, right? So what we did, it was on different scale, now we bring it to a common scale and with a mean of 0 and standard deviation of 1. Are you able to get it? Everyone, are you able to get it? Yes, very good. So we'll now, this is the same thing that we will do with the different methods, okay, and it will the same thing. Okay, so let me give you today's context. So